So let's talk about Kepler's law. And Kepler was a physicist who had a big contribution in the mechanics to understand the mechanics of planets rotating about the sun or the solar system. And he gave three laws, and these are in a combined way called Kepler's law. And we already have solved a problem where we assumed that there were two binary stars that were moving around each other about a central point, and this is because of gravity. It's the gravity that provides the centripetal force so that they keep moving in a circle. As a matter of fact, even in solar system, if this is sun and this is earth, then the force of centripetal force actually is provided by force of gravity. So earth is being attracted towards the sun, and this makes the earth to continuously fall towards the center in a circle. And is the gravity that is providing the centripetal force. But it's not always a circle. The movement of the earth around the sun is not an exact circle. In fact, none of the planets actually move in exact circular orbits. These orbits are actually elliptical. So the planets move in something like this, in orbits which look something like this. So here is sun, and this is this planet is moving in this elliptical orbit, and this is called an ellipse. This ellipse has two foci, one here and one where the sun is sitting. So the star is present at one of the focal centers. It's called focal center of the ellipse. Also, this axis is called the major axis of the ellipse. So this is major axis, and this axis is called the minor axis. Okay, so ellipse has these properties: two focal points, or focal centers, and a major axis and a minor axis. For a circle, these two focal points are at the same point here, somewhere in the center, and major axis has the same length as the minor axis. So circle is just a special case of an ellipse. Okay, so given this, that a planet moves in an ellipse, on an ellipse around a star, Kepler gave three laws. First was that all planets move in elliptical orbits with the sun at one focal point. So all planets move in elliptical orbits with the sun at one of the focal points. Second, the radius vector drawn from the sun to a planet from the sun to a planet sweeps out equal areas in equal time intervals. What does that mean? It means if this is the ellipse, and this is where our sun is, then the area swept by the radius vector, and this is the planet which has gone from here to here, and let's say it does it in time t, and let's call this area A1, and let's say the planet goes from here to here, in fact let's say somewhere here, and it also does it in the same time t, and A2 is the area. Then A1 equals A2, which means the planet will sweep out the same area in equal times. So here it moves from here to here in time t, and here in this case it moves from here to here in time t, such that the area swept by the radius vector, this is the radius vector, from the sun to the planet, the area swept by the radius vector is same in both the cases. And this is by virtue of conservation of angular momentum. You see there is no net torque acting on the system. So the angular momentum of the system is conserved, which we can understand from here. So if you, let's say, this is the planet which moved from here to here in time dt, small time, and it covered an area, an angle d theta in time dt, and we are choosing dt and d theta small because we assume that radius vector stayed constant throughout this motion. Here you cannot say radius vector stayed constant, but if you choose theta to be small, which means very small, thin, very small change, then in this small change in theta we sort of assume that radius is constant. So if that is true, what is the area swept by the radius vector? So if this is the radius vector, a straight line, another straight line, this is a straight line, I am not able to draw it probably, but these are straight lines. This angle is d theta, and it does it in time dt. So what is the area swept? You see the area swept is, this looks like a triangle, but this is an arc of a circle. This is an arc. We know we cannot treat it as a straight line, but for smaller distances, for smaller d theta, this is small and this is small, we can treat that as a straight line. So this is sort of like looks like a triangle, and this is nothing but base into height. What is the base? Well, base is what is this distance? This distance we know is r d theta, and what is the length here? So this length is times r. So this is nothing but r square d theta, and it says it covers same area in same time. So what does that mean? Which means this is dA, which is r square d theta. What is dA over dt? This is r square d theta divided by dt. And if you multiply the whole thing by a constant, this is mass of the planet, then dA over dt equals mr square d theta over dt. Now you can clearly see this is nothing but I omega, right? Mr square is the moment of inertia of the planet about the central point, about the focus, and d theta over dt is angular velocity, which means because angular momentum is a constant, because I omega is a constant, dA dt is a constant. If dA dt is a constant, which means the area swept in equal times is the same, which means dA dt is a constant. That means delta A is going to be, let's say constant is C times delta T all the time, because it's a constant. You don't have to integrate that. All you have to do is multiply, make it bigger, that's it. So instead of using dA, you can use delta, which means a bigger number. So similarly, dA2 is nothing but C delta T. So unless you do not change the time, area is going to stay constant, which means delta A1 is same as delta A2. So this is by virtue of the by virtue of the conservation of angular momentum. Okay, and there is one more Kepler's law, and that is, the third one is, we don't have a space, so we have to use a new page. The square of the orbital period, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit, to the cube of the semi-major axis of the elliptical orbit. What does that mean? Which means if this guy is moving, this planet is moving about the planet, then it takes time t to complete one orbit, and this t square, if you call this a, is the semi-major axis, then t square is proportional to a cube. And we can actually clearly see this for the case when orbit is a circle. If orbit is a circle, then we can certainly derive this proportionality thing. How? We see that, again, we invoke the same formula, that g, let's say ms is the mass of the sun, mp is the mass of the planet, gms mp divided by r square, r is the radius, equals, we know as this gravity is going to provide the centripetal force, which is mv square divided by r, and we also know the time it will take to complete one circle is going to be, circle has a circumference of 2 pi r, so t is the time period, so 2 pi r is the circumference which it has to travel, and we know that velocity is v, so this is the time it will take to complete one circle. And if we rearrange this whole thing using this equation, we will get this. This is what we will get, which means t square will be equal to this rq. Okay, so, and you see the t square is proportional to rq, and this is the proportionality constant. Well, we proved this for a circle, but Kepler said that this is also true for an ellipse. And for the case of ellipse, t square is proportional to a cube, where a is the length of the semi-major axis. So this is a. Let's solve a small problem quickly. Let's say for the first case, let's say time period of a planet is 1 year, let's say it's Earth, and the length of semi-major axis is, let's say it's e, and length of semi-major axis, I don't know how much it is, but let's assume it to be 10 to the power 6 meters, and let's say there's one more planet, and let's call this Mars, has time, or let's use some other planet, let's say it's Saturn, and it uses 4 years to complete one circle. The question is, what is the it's not acceleration, it's the semi-major axis. What is AS for the Saturn? Don't trust these values. I have made up my own values. Please check on internet for the right values. So what is AS? So we know t square equals proportional to a cube. So we know we can, let's say the proportionality constant is something c. So you can say t square equals ca cube. This is the proportionality constant, where we already know the proportionality constant for a circle. We do not know for an ellipse, but let's say it's c. Then we know te square equals cae square. This is going to hold true because of proportionality. Also we can say ts square equal to the same proportionality as square, as cube I mean. And you define the first one with the second one, or second one with the first one. Let's say this is first and this is second, this is first. You divide second by first, we get as over ae cube equals ts over te square. So that gives us as over ae cube equals, and we already know this, 4 over 1, this one 4 over 1, which is 4 for the 16, and then we take a cube root, and that gives us as equals ae multiplied by 16 to the power 1 over 3. So this is some number, I'm not sure how much it is, but it should be more than 2 on less than 3. So let's say 2.5 or something near that. So as is going to be ae, which is 10 power 6 multiplied by this number. So this thing here is nothing but a result of this proportionality. So you may get problems like these in your exam.